Okay, polar molecules. So we have to determine whether or not we have polar covalent bonds present first. So for example, if we look at the carbon-oxygen bond, you subtract the low electronegativity value from the high electronegativity value, and if it's greater or equal to 0.5, it is polar covalent. So our carbon-hydrogen, 3.5 minus 2.5, so the difference in electronegativity is 1. So that is a polar covalent bond. Carbon-hydrogen. Difference in electronegativity. Hydrogen is 2.1, carbon is 2.5, so the difference is 0.4. So it is a non-polar covalent bond. So no dipoles. So this one will have dipoles. Polar covalent has dipoles. No dipoles for non-polar. Nitrogen and hydrogen. Nitrogen is 3.0. Hydrogen is 2.1. So the difference in electronegativity is 0.9. So it's a polar covalent bond, and you would put dipoles on it. So we're going to do dipoles as vectors. So carbon, oxygen. The oxygen has the greater pull, so you would draw your dipole as a vector, as an arrow going towards oxygen. Oxygen's a little bit negative, carbon's a little bit positive, so if we put a line over the tail of the vector, it makes a positive sign. Carbon and hydrogen, there are no dipoles because it's 0.4, so you would just leave it alone. And then nitrogen and hydrogen, you would do a dipole because it's polar covalent. Nitrogen has a stronger pull than hydrogen, so the vector arrow goes towards nitrogen. Hydrogen's a little bit positive. So this is how we're going to draw our dipoles. So NH3, our Lewis structure will look like this. Our structural formula will look like this. Structural formula is Lewis structure without the lone pairs of electrons. So this is our Lewis structure. And this is your structural formula. Now pay attention to the question, because it might ask you to put the dipoles on the Lewis structure. It might ask you to put it on the structural diagram or the structural formula. So pay attention. All right, so dipoles. We know this is a polar covalent bond because we just did the example. So these are our vectors. These are our vectors. So when we add these vectors, there are rules to follow, and if you've taken physics already, you know this. So we're going to call this vector 1, vector 2, and vector 3. These are all equal in size because they're the same difference in electronegativity. So what we do is we add the vectors together. So pick one vector to start with. So we're going to start with vector number 1. So it goes in this direction. Now, when you add a vector together, you add the tail of the second vector to the head of the first vector. So this is the head, this is the tail. So my second vector, I'll do it in a different color. goes back in the opposite direction. It's actually right on top of the first one, right? It really is right on top. And then vector, so I'm right back at the start, but I've got to add in vector number 3. Vector number 3 adds to the tail, adds to the head of vector 2. So now I've added that vector. Now, to determine whether or not you have a net dipole, you decide if you've got a net vector. This was our start. This is our finish. If you finish where you start, you have no net dipole and you are nonpolar. So, if no net dipole, you are nonpolar. If there is a net dipole, you're a polar molecule. And to determine if you have a net dipole, did you finish in the same place that you started? If the answer to that is no, you have a net dipole. And your net dipole goes from the start to the finish. So this is the net dipole for this structure. Get rid of that. So this is our net dipole. You go from the start to the finish. So ammonia is a polar molecule. And it's polar because there's a net dipole. And this is how you show your work. Second example was carbon dioxide. And we figured out that our Lewis structure looked like that. So our structural formula looks like that. It's linear. Okay, linear means a straight line. That means from the middle of our terminal, our ends, in this case our oxygens, through the middle, it makes a straight line. So it's linear. Okay, so in this case, difference in electronegativity difference in electronegativity 3.5 for oxygen, 2.5 for carbon, so each dipole is 1. Oxygen has the greatest pull, so the vectors go out towards oxygen. And these are going to be equal in size because they have the same value of 1. Now these happen to be equal and opposite, so what's going to happen if this is vector 1 and this is vector 2? If I lay down vector 1, vector 2 is equal and opposite. So here was my start, and it's also where I finished up. So carbon dioxide has polar covalent bonds, but it is non-polar. It is non-polar. There's no net dipole because they cancel out. They're equal and opposite in direction. So this is why shape is important. You have to get the right shape for your Lewis structure. So ammonia had polar covalent bonds and ended up with a net dipole, so it's polar. carbon dioxide had polar covalent bonds, but they canceled. So it's nonpolar overall. Okay, carbon tetrafluoride. So our Lewis structure would look like this. So our structural formula would look like this. So, difference in electronegativity. We're going to have fluorine, which is 4, carbon that's 2.5, so our difference in electronegativity is 1.5. So that's very polar. That's very polar. So we have dipoles. So the fluorines have a greater pull, so they're a little bit negative. Carbon's a little bit positive. These are all the same length because the difference in electronegativity is equal. So if we did our vector diagram for this, 1 went up, 2 went to the right. Should label our start. Three went down, and then 4 went to the left. So we are back where we started. So this has polar covalent bonds, but it is non-polar. There's no net dipole. The dipoles cancel. CH4, difference in electronegativity between carbon and hydrogen is 2.5 minus 2.1, 0.4. Not enough for the caramel secret. Here's our Lewis structure and our structural formula. You leave it alone. There's no dipoles. There's no polar covalent bonds. It's non-polar. It's non-polar because the bonds are non-polar. And that's how you figure out if your molecule is polar or not. You look and see if there's any dipoles, any polar covalent bonds, and then if your dipoles cancel, you're non-polar. If your dipoles don't cancel, you're polar.